Good afternoon and welcome to today's webcast presented by Machine Design, New Equipment Digest, and EHS Today. Our topic today is validation of machine safety functions, sponsored by Schmersal. I'm Bob Vavra with Informa's Design Engineering and Sourcing Group. Let's talk about how you can participate in today's presentation. If you have any technical difficulties, simply hit F5 to refresh your webcast console. If you still need assistance solving common issues, please click on the yellow help icon below the slides. We also welcome your questions during today's event, and we'll answer as many as we can during the Q&A session that'll follow the main presentation, so feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on all of the websites within the next week. You'll be notified by email when the archive is available. So let's meet this afternoon's speaker. Mike DeRozier is a TÜV certified functional safety engineer for machinery. His more than 20 years of experience includes everything from control systems and control engineering to the design, building, and integration of full machine control systems. You can learn more about Mike by clicking on the blue speaker bio widget on your console toolbar. Mike, good afternoon. We're looking forward to a great presentation, and safety is a very important topic to all of us. So we're looking forward to your knowledge here this afternoon.
Great, thanks, Bob. Appreciate it, and thank you everybody for joining us this afternoon. I know we've covered a lot of different types of topics with safety, and one of the topics we thought we'd cover this go around, because more and more questions are coming up as a result of this, is the validation of machine safety functions. And to even start talking about it, understanding the word validation sometimes can get a little tough, just because validation can mean different things to different people or even different industries. For example, if you think about pharmaceutical or chemical facilities, when they talk validation, they may be looking at more of validation of the process and the product and what they're doing, and it gets into a significant amount of detail. And even though it's along the same lines, with what we're talking about, machine validation is different when we talk with the safety functions themselves. So one of the first things that we want to do is talk about the definition of validation. And I pulled this from online from the Merriam-Webster dictionary and what the actual definition of validation is. And it doesn't give you a lot of details aside from what you see there, an act, a process of validating. What does that really mean? So I pulled the synonyms for them, and what you see there is a lot of what we're talking about with machine safety functions. When you look at some of the standards today, and probably one of the ones I'm going to reference most would be ISO 13849, and specifically Part 2 when it comes to validation, because that standard's written around that. It's complementary to 13849.1 with the safety functions themselves for machines when we talk the safety-related part of the control system. But when we think about that validation, we're starting to see it pop up in other standards over the last several years as well. For example, anybody that's into robotics, robot cells, it's written in the RIA 1506 in the 2012 edition. It's in the ISO 10218 over in Europe. They talk about verification and validation of the robot and the robot cell and the need for that. And we're seeing that more and more. Whether you're requesting it, you're having OEMs do it, or customers are requesting it from you, what does that really mean? And oversimplifying it, we're proving out the safety system. But there's different ways of looking at that and how to prove it out. So let's look at what a safety function is and how that is really defined when we look at it from a machine perspective. The safety function is one of those things that is designed that whether it's a single channel or dual channel system, where it occurs, what failures can occur, but ultimately it's a means of trying to mitigate the risk factors and what the results can be. So this definition you see on the screen right now is verbatim right out of ISO 12100 and talking about that. But when we talk safety functions themselves on an actual machine, what we're actually talking about is that SRP/CS, which is the safety-related part of the control system. And you may hear it in a term of performance levels being PL, which is out of ISO 13849. You may hear it as SIL levels, which stands for safety integrity levels, which you see out of IEC 62061 or IEC 61508. But ultimately, we're trying to get to the same thing. We're looking at a safety function of machine and building an architecture around that, being our control categories, and looking at statistical probability of dangerous failures that can occur. What does our risk assessment say we need to be, and what are we looking to try to do? So when we look at safety functions within themselves, what we're looking at is what are the actual safety considerations or the design of what functions are on the machine. We're not talking about non-safe, normal machine operation, normal stop buttons, or what product or widget is being created as a result. Okay, what we're looking at is the actual safety portions. So if we think about some of the safety functions on a machine, an emergency stop circuit is a safety function. When you hit that e-stop push button that's on that operator panel, what happens to the machine? What puts that machine in a safe condition and prevents it from restarting as a result? Does it shut the motor down? Does it dump pneumatic air? What's the risk assessment say that that safety function needs to do? A guard door interlock. You could have a perimeter guard around the machine, maybe with 3 or 4 doors. Opening up one of those doors, what does that do? That is a safety function. You could have a palletizer where you have pallets that are being skidded up and shrink wrapped, whether it be a robot or a pick and place type of system, but it needs to exit out. You could have a muting light curtain, which would be a safety function on the system. So when you look at ISO 13849 Part 1, they give you a great list of what safety functions can really exist on a machine and going through that decision tree to determine the levels. So when we look at the beginning cycle of a machine a lot of times, and please bear with me as what you see on here is not comprehensive, it's just some examples of what's typically being looked at. But when we have, whether it's a OEM or end customer specification, the very first steps are what's the scope? What does the machine need to do? What kind of automation is involved? Do we need robots in there? Is it simply an assembly machine? Is it a packing machine? What are we really doing? What standards are going to apply? What are the safety functions that we're putting into place? We determine what levels they need to be at. So we may determine that this particular safety function needs to be a control category 3 architecture, which has some redundancy and monitoring to it. So based off of that, we designed that architecture and looked at implementing. What guarding requirements are on there? What does the machine need to do? How many widgets does it need to produce as a result? Well, the next step is we actually fabricate the machine. We get it built. We put the guarding in there. We implement those safety functions to what was designed based off of the schematic and the initial risk assessment. And we make sure the machine does what it's supposed to do as a result. Well, then we get to that point where we're ready for factory acceptance testing. So the end customer comes in, looks at that machine, it does everything it's supposed to do. We get our 100 widgets a minute. we get it shipped and on its merry way. What we're not seeing in this list is the validation. Where is the validation, and what do we need to do with validation? What needs to be validated, and why are we even looking at validation as a consideration with machine safety? If we designed it right, isn't it okay? Well, the issue comes down to, is it really okay? Was it designed properly? Was it installed per the design? Did that get checked out? So when we talk validation of machine functions, what we're actually looking at is, in essence, potentially two areas: applying the analysis and actually performing or executing functional tests, throwing the faults into the system. And then when I say into the system, into the actual safety function that the safety function's designed to detect and still work. Did it do what it was designed to do? Did it shut the machine down, and did we detect that fault? So the example I gave just a few minutes ago, if we had a safety function that needs to be a control category 3 where we have redundancy and monitoring as a result, did we actually introduce some of those faults because we're supposed to have some level of monitoring as a result? So based off of that, did we do any of the validation to prove it out? Well, we're looking at these aspects, applying the analysis. So what we're talking about there is looking at the overall design. So our validation actually starts early on. We want to try to get it going when we're in those design phases, because with trying to do some of the analysis of what we have, is it the right thing? What's the risk assessment covering? Did we start doing calculations to know that, hey, based off of our probability of dangerous failure per hour, is our design going to meet that? Because it can get very costly and can have significant delays that you build this system up and add these safety functions, come to find out when it goes through the validation at the tail end that, oh, you know what, this really wasn't the right component to use, or this wasn't the right architecture we needed to put into place. We have to change that now after we fabricated it. So the earlier in the design phases, the better it's going to be. So you're going to review that safety-related part of the control system. Look at those quantitative numbers, being the statistical side of it. What's the probability of dangerous failure per hour? How much diagnostics are you picking up, or safe fraction failure, depending on the standards that you're using? And then when we talk about the execution of functional testing, what you need to do is develop a test plan. And I'll go through more details of both of these as we talk through them, but actually introducing those faults. It could be open circuits, short circuits, and where's the actual test results? It goes in that test record. So what we start looking at is the big questions. One of the first ones out of the two that comes up is, can we validate through design and not have to do any functional testing? Or do we really have to perform functional testing? What we look at is, with both of these questions, the answer is we're actually doing both to the best of our ability when it comes down to validation. It's not one or the other. They're two pieces to the puzzle to put together to prove that concept out. So what are we looking at the end of the day? Well, I threw up an example up here. It's a guard door interlock. It's a single guard door. We open up that door, which shuts down a single 3-phase motor. Well, based off of what we're using and how often we're doing it and the type of circuit we're putting into place, when we look through some of the standards, and here I'm going to specifically reference ISO 13849, that's where this decision tree has come from, is I may have looked at this function, and based off of the usage and their frequency of exposure and how bad somebody can get hurt, I designed a performance level D in my risk assessment here. I've said this safety function, I have to achieve a performance level D. I'm already starting the validation process now, because when I started the design and the selection of those components and the architecture, that category 3 architecture I'm designing, I'm looking at several different aspects now. We identified that safety function. What are we trying to do? How many safety functions are really on the machine? Do we look at what that decision tree is for each one of those safety functions? How are we getting there? Meaning, what architecture do we put into place? Do we put the right category B, 1, 2, 3, 4 architecture? I may be just in those phases right there. Next thing you see on that list is the statistical data. What's the reliability factors? What's my diagnostic coverage? I may not have gotten that far yet. So your analysis portion of the validation pauses right there till you get to that point. However, you don't want to wait until you've actually ordered all the components, wired it all up, got it into the system, and then start doing the calculations, because you may find that based off of the usage, maybe the circuitry is okay, but that particular switch that's in the circuitry cannot handle the life cycles that you're trying to accommodate for that safety function. So as a result, we may have to put a different switch in that circuit. So we're best off trying to start looking at the calculations once we get through the design and look at what are we possibly going to achieve. Now, at the end, you're going to verify that. You're going to check those calculations. Did you get what you really needed to get? But that's not the first place you want to look at it. You want to look at it right after you get that design done. What other documentation really needs to be part of it? Again, these are just some examples. This is not all encompassing, but with reviewing that documentation, do you have all the proper schematics? We're not just talking electrical. Even though this example is electrical, because we're just shutting down a three-phase motor, that's the safety function by opening up a door, shutting down that three-phase motor. However, maybe you have hydraulics, pneumatics. What are you doing there? Did you start looking at the designs of that? What safety levels do they need to be? Don't just stop at the wire. With any system, you may not be able to design a system without considering fault exclusions or potential systematic failures. You want to look at that. And then part of this, in the applying the analysis phase, we're developing the validation test plan. And what I mean by that is, how much are you validating via design, and how much are you validating by actual functional testing as a result? So when we look at that, we're going to look at a test record, and I'll show you an example of one particular fault when we look at our system. So in this particular safety function, basic circuit, oversimplified, we don't have everything in here that we would normally see in a machine, but just a simple concept of what that safety function is. We could have a key interlock switch using 2 channels into a safety controller, and then the output of that is 2 mechanically linked contactors that are being monitored by the safety controller to ensure the safe shutdown of that 3-phase motor. We have our design now. We know our statistical data, and we start doing our calculations. And again, I'm going to reference 13849, but we may be looking at what are those different values. We look at our common cause failures. We look at our diagnostic coverage capability. We look at our hardware reliability, but ultimately getting to our PFH, our probability of dangerous failure for that safety function. Well, as we're reviewing those numbers and we're doing the calculations, and we look at that and ensure that those calculations are correct, what are we really doing? We've already started the validation process. And I know that may sound simple, but what you may find is a lot of that is not being checked. You want to check all along the process and have those checks and balances, because ultimately part of applying that analysis may be looking at it from an overview perspective to say, hey, I have this control category. This is what was required in my design. Did I actually achieve it? Do I have a Category 3 architecture in there? What's my justification or rationale for saying that it's Control Category 3? In this particular chart that you're seeing in there, CCF refers to common cause failures. In ISO 13849, any Category 2, 3, or 4 system, you have to have a score sheet that scores 65 points or higher. So what we said is, because it was Category 3, was CCF even required? Yep, what did we achieve for a score? We got 75 points. We're okay as a result. What were we looking for as a minimum for our diagnostic coverage and our hardware reliability? Did we get there? What did our PFH come out to? Our probability of dangerous failure per hour. What did the number range come out to? We were looking for a specific range for that specific performance level. Hey, maybe in this case we ended up overachieving. Great. We overachieved. That's fine. There's nothing wrong with that. But what would have happened if we went through all this design and did all this and we found out that we didn't get our CCF? There's something wrong or missing in that design. Our performance level ended up being a performance level C. Why is that? Maybe our DC ended up being too low, or our hardware reliability of a specific component in that safety function was too low for what we were trying to achieve for a PFH value. And maybe going back and redesigning, but it was doing that check to prove it out before we actually did a full installation and confirming after the installation. This is all applying analysis at this point. We're not even doing functional testing yet. This is checking over the design. Do we have the right documentations? Are the schematics correct? What are the things that we need? Now, that doesn't mean that once we do that and we're ready for fabrication, applying analysis is done at this point. So applying analysis is through the entire stage of that machine and in conjunction with the actual functional testing. So what do we mean by functional testing aspect? Well, part of it is when we're applying analysis, we're looking at what our safety system is designed to do. It's designed to detect single faults in our safety function, still provide that necessarily shutdown, and prevent it from restarting. So what we need to do is develop that test procedure or a test plan. What are we actually doing? What information is required? It could be who's doing the testing, what date was the testing done, what's the actual procedure. So in the example I have up on the slide here, and there's 100 different ways you can put this in a Word document or an Excel spreadsheet. There's not a distinct format that says you must do it this way. It's, do you have all the relevant information and the testing in there? So here what we're showing is what's the device? Well, according to the schematics, this is labeled door number 1, and the nomenclature or reference on the schematic is 1010LS. Great. We put that information in there so we know exactly which switch we're testing. What is the test? Short circuit on channel 1. So what is the actual procedure? It could be placing a jumper on terminal blocks in the panel because of how the wiring's landed. It could be out at the switch. It could be at the safety controller. Wherever you're testing, you want that document. What's the test procedure, and what should the result end up being? All right, in this case, if we put a short circuit on that first channel, the motor is still supposed to enter that shutdown, power disabled from it or removed from that motor starter. Motor, no power, doesn't spin, we're stopped. But if we try to reset that with that fault in there, we won't allow a reset to occur until we fix the failure. Well, now what are the test results? Pass or fail. You're not developing a validation plan for things that you do not detect. You address that kind of thing in your analysis phase to say, hey, we have fault exclusions, we're not detecting this, and this is why. You have it properly documented. But wherever you can detect something, that's what you want to test for. Maybe you have a spot for additional notes that maybe there was something that you felt that needed to be added in there as a result. But we have our pass-fail check mark. Whenever we have fail, we know there is something wrong. So what do we mean by that? Well, if you look at the schematic that I originally put up there, here's our schematic, but hey, there's that jumper wire between S11 and S12. I know some of you are probably sitting back going, wait a minute, actually introducing an electrical short circuit, isn't that a bad thing to do? Isn't that unsafe? We're talking safety here. The one thing I can tell you with these types of safety circuits, they're all low voltage. They're 24 volt DC. They're current limited. They don't create arc flashes like we're talking shorting out a 120 or 480 volt AC line. We're not talking about doing that kind of thing and not having proper circuit protection in there. You're trying to introduce the faults that you know the safety circuit is supposed to be functional on. So based off of that, we can put a short circuit in here and short out this 24 volt low current source, open up that door, and see if the controller does its job. Did it detect that? Because that safety controller is designed to detect that dry contact switch and look for those faults. So look for open circuits, look for short circuits. If your safety controller is designed to do cross-short recognition, a short between two channels, you can introduce that. You have to really understand the safety controller and how it works and how does it recover from that cross-short that you implement. But that's where you list these different types of faults. So if we look at just on this switch, forget anything else here, but if we look at the switch, what faults can we introduce? We can put a short circuit on channel 1, an open circuit on channel 1, a short circuit on channel 2, an open circuit on channel 2. Because we're doing cross-short recognition, we can do a short between two channels. Do we detect those failures? Now, here's where the questions really come into play. So, can I not do that by analysis versus functional testing? Functional testing's there for a reason. Just because your analysis showed that it should be okay doesn't necessarily mean that it was wired that way. Or if you're dealing with more complex systems that use programming, that it's configured that way. It's been programmed or parameters set up correctly. Doing the functional testing becomes very important. Now, there's times that you may not be able to do functional testing. There's times that you may combine functional testing with validating design as well based off of the components, and we'll go through a couple of those scenarios. But jumping into that, when we look at mechanically linked contactors, the whole idea behind a mechanically linked or positively guided contactor or relay, if you get a normally open contact that welds, the normally closed has to maintain a gap of at least a 0.5 millimeter or more from closing again. Why? If you look in the top right-hand side of that controller underneath the reset, that's where we're monitoring the contactors in this particular circuit. So if the first contactor were to weld, that normally closed contact stays open and it prevents us from doing a reset to allow that motor to turn on again. Well, with a switch, we can simulate a failure by creating a short circuit. How do we simulate a failure of a welded contact? That's not straightforward. We cannot force a contactor to weld. Is there something that we can do? Maybe we can apply 24 volts directly to that contactor to keep that contactor energized when we open up the door to simulate the failure, because what are we looking at? We're looking at, are we monitoring that contactor? And here's where you can get into your validation by design in conjunction with functional testing, because by pulling the information from the contactor manufacturer that claims that it meets this certain IEC particular number for being mechanically linked. This is rated for safety applications, and combining that with your validation report says we are simulating a failure by doing this to make sure that that is being monitored, but an actual weld of contact, if it were to occur, this is what we're getting from the manufacturer's information and test data and things like that. So we're combining the two as a result. Now, this is all well and good, but ultimately, that's a simple circuit. We know that there's a lot of safety functions out there that are not as straightforward. So here we may have a series of 12 different doors that are tied in, and great, they're landing the terminal blocks. So where can we do our functional testing as a result? What functional testing are we doing? Well, it might be the easiest thing to do right in the junction box or right in the bottom of the control enclosure where the terminal blocks are located, is all the external switches coming into the bottom of the control enclosure, landing on those interface terminal blocks, and then from there, they're going up to the panel, to their safety controllers, and doing what they need to do. So maybe that's the easiest place to do your functional testing, but then what type of testing are you doing? So when you do an electromechanical switch like that standard key interlock in the previous example, you're doing those opens and short circuits. Well, what if you have switches like these, which are actually more electronic, like RFID type of safety switches? It's not as straightforward of doing some of the same type of testing, but it's similar. You can do short circuits on OSSD outputs because the switches are supposed to detect that and still provide your shutdown. But you have to determine right back to in your design and your analysis portion of it, what is the actual test plan? Meaning, what faults are you going to have? What are you going to introduce? How are you going to introduce them as a result? It could be that based off of these electronic switches, you may test one or two, and should you test the other ones? It really depends on the system. If you can, it's best practice to do that. If you can test a few of them and prove it out and then go by knowing the color codes and the wires and how they're landed, is that fully functional at that point in time? It depends on your analysis and how you're justifying it at that point in time. But ideally, you want to try to do functional testing on all the switches if possible and if needed based off of your validation plan. That's where it all comes back to. So what other considerations do we take into account here? Here's the list. Looking at software, we're getting more and more technology out there now. I'm sure all of you have seen it. We have programmable safety controllers. We have safety PLCs. We have safety I/O on standard controllers with piggyback controllers. We have safety over communication networks now. So we have safety over Ethernet. We have safety over Profinet or Profibus. So there's different protocols out there for communicating safety technology. But one of the biggest ones is software and the programming, because too many times this should be thought of, but it's not. And thinking about how something's programmed, because even though you have say as an example, as a programmable safety controller, you have safety function blocks. Or in a safety PLC, you have safety function blocks. But those function blocks may or may not be able to be configured. What is the configuration? Did they get checked against it? You could have a scenario within a company or a machine manufacturer where the controls group designs all the electrical controls. They put the programmable safety controller in there, how it's wired up, know the control architectures, but the person that's actually doing the programming is in the software group. Well, the software group is not educated on the safety levels and what needs to be done. We could have a mismatch there as a result. But then with all this technology, it may start getting a little harder to actually introduce faults for fault testing. And one of those would be, what if you have a system where you have quick disconnects? How can we validate that? That might be difficult as a result. Just because it may be a little bit difficult, but the difficult may be more of a perception initially because, hey, I can't cut a cable. Well, no, but you can get a spare cable and create fault introduction on that so you can test each switch and splice it together with that cable and that switch to be able to do different types of fault testing on those switches. The quick disconnect is great because it makes it more of a plug-and-play system, makes it more efficient, less cables that go back to a cabinet or a junction box, just like we see in standard I/O. We're seeing that with safety I/O now. But it might mean we cannot just simply test every switch at a junction box because we have an external connection system. How do we introduce the fault? It all comes back to being part of that design of that test plan, or the validation plan being the test, and going from there as a result. When we look at software and function blocks, all right, here's a page of code that shows some logic of certain safety devices when they're triggered to allow safe torque off to engage and do different things with AND gates and OR gates. So that's all great. But based off of that, can you follow that flow and say that this is all okay? They're safety function blocks, or they're safety inputs, or single inputs to them. But what does that really come down to at the end of it? Well, when we look at it, if you look at the tables I'm showing on the screen right now, in that exact piece of code, on the e-stop, that's an input to that code, you see that that e-stop function block can actually be configured different ways. If you look on the left one, and we're talking the same exact function block for the same program, we've determined that we need a Category 3 architecture, so we have redundant inputs that we're looking at cross-short recognition. Well, if you look at the block on the left, that's configured for one normally closed input, and the input is turned off for the test pulses. And that's what you see in the very first line under inputs, under type. And then where it's grayed out, the cross-circuit check is off. Well, the actual configuration and the parameters of that function block needed to be what was on the right-hand side. Two normally closed on the inputs and which inputs were there, and doing the cross-short recognition by using T0 and T1. But if you didn't do the validation to look at that, how do you know your safety controller was programmed properly for your e-stop, your guard door interlocks, your light curtains? If the programmer only configured for a single channel input and it needs to be dual channel, we have an issue. We're finding that in the validation process. Why is all of this important at the end of the day? I have several examples of projects I worked on with customers where I went into either the end user to look at a piece of equipment that was supplied and perform validation, or got involved right from the OEM from the get-go before the FAT came in to do the validation testing, and we did these functional tests. I know of 3 separate occasions where doing that functional testing came out to show or find issues as a result. And what we found in one particular case where everything looked like it was working, but introducing one single fault opened up the door, the machine kept on running. And when we looked back, we verified that the machine was wired per the schematics, but when we looked at the installation instructions of the manufacturer's switches and controller, we found that the design was not correct per the installation instructions for the level they were trying to reach. By putting one wire on one terminal versus another, it changed the function of the safety controller of a dual channel with cross-short recognition, which is what the intent was, to a single channel without. So that single fault could have led to an unsafe condition. But by doing the validation, we were able to prove it and find it out. In other cases, we found because there were integration lines and the machines were being supplied by different manufacturers, but it was one integrator putting them together. We found cases where jumper wires in terminal blocks were left in, even though the external e-stop circuit was wired in. They forgot to remove the jumper wires that came from the original OEM. So when they went to do an e-stop, to do a global e-stop on the machine, only that machine shut down. None of the other ones did as it was supposed to. Found the jumpers, removed them, but it was by doing those visual inspections. In another case, what we found was a case where the e-stops are all dual channel. It all went back to a programmable safety controller. Programmer had not coded it properly, and only half the e-stop circuitry was working because of the way the function block was configured. Well, now we start getting a little bit more complex because we have safety over a network. What's coming down the line as a result when we look at this? So safety over networks. I had mentioned safety over Ethernet or Profinet or Profibus. Well, we got safety on OSI-Bus. So this is an OSI safety network. Well, how do we throw faults into there? This might be doing more by design and less functional testing because of what information we were able to get from the manufacturers because of the testing that was done at the factory in those particular fault examples and what's being picked up. Doesn't mean we don't validate the software at all. We still need to do that. How are these function blocks being used? How are they being configured? Is the slave addresses correctly? Can we physically check that by putting an addressing module on there? We absolutely can. Can we simulate failures of those contactors? Absolutely we can. It doesn't mean that we completely eliminate functional testing. It just may be different functional testing as a result. So when we look at more of a summary now, look at the importance of validation. I just given a couple of examples of where validation really, really helps. So hopefully you validate and everything is perfect from the get-go. That's the ideal scenario. We know mistakes can happen. They're not intentional. Errors can happen. Wiring changes. The design of the wiring might not be correct. When you look at most manufacturer safety controllers, they're much more universal today than they ever have been. Well, because they can be wired and configured different ways, just because it's rated Category 4 PLE, it still comes back to what devices are you connecting to it and how it's being wired to determine what your overall control category is and what your overall performance level is for that entire safety function. So that validation piece is so important. Remember to start early. It's not at the end when everything's already made. Too many things can have passed by that you could have captured in the design phases. So you start the analysis portion of validation in the design phase and keep it going. It doesn't stop there. Now, what you see with validation is, and specifically at ISO 13849, they call out that validation should be performed by somebody independent of the design. But they do take a specific note. It doesn't mean you need a third-party consultant coming into your company to do that. But if John designed it, maybe Jane should be the one that looks at it and validate. They're colleagues, they work together, but somebody different than the design so they can look over everything and prove it out. It's a good practice to get into. What is being validated by design? What are you taking based off of manufacturer's installation instructions and declarations of conformity, or what standards they meet, and how are they doing it internally with internal monitoring? And what are you doing by design? And then what can you do as actual implementation? So the functional testing itself. What faults can be introduced, which leads you into developing that whole validation plan, making a test record. What faults are you going to introduce? go and do that and determine that they've all passed and document that, so perform that functional testing. And we're going to see technology keep growing from there. So at this point, what I'd like to do is, I think we're at time, we're going to open up the questions.
Very good, Mike. Great presentation, a lot of great information in there, and as you would expect, we've got a lot of questions, so we're going to get right to those, get to as many as we can. If you've got some additional questions, please type those into the question window on the side of your screen and hit the submit button. And while we're answering your questions, please also complete the feedback form, which is located at the bottom of your screen. As I mentioned, we've got a lot of questions from the audience. We'll start with Crystal Gunn from FCA. Would you suggest we have OEMs or integrators document the risk assessment and the DEMA at the design phase and provide that as a deliverable to the end user?
What we're starting to see is that is becoming a requirement in different standards. I can pull out one specific one, is the ANSI RIA 1506. That is in two parts, and it's a mirror image of the ISO 10218 Part 1 and Part 2. So Part 1 is for the robot manufacturer, Part 2 is for the integrator. And when you look at it, one of the requirements in there is for the integrator to develop a risk assessment and perform that risk assessment. It doesn't say anything specific about Systema, because Systema is one tool for doing that. But as an end user, my recommendation is, if that's information that your company is implementing, to say, as a company, we are adopting this standard, we are adopting ISO 13849, that should be part of your bid proposal to your OEM, that these are the things that we want to have seen as part of the machine and then part of the deliverable. We want to see the risk assessment. Maybe the OEMs do more informal and they don't do it documented. Maybe they need some assistance with that, that you have a risk assessment template that you want them to use. The RIA developed a technical report, TR306, that works off of a task-based risk analysis. You can implement something like that to do your task-based analysis. Just because it's for robots doesn't mean it's solely for robots. I've seen people use that format for other machines besides robotics as well. So the more you can require it as a company, when it comes down to legality of it, nobody's required to provide you that. So I should say a machine builder is not necessarily legally required to do that. If it gets into a court of law, can you prove that? Is it good practice? Yeah, absolutely. But that also leads the OEM to getting more familiar with it. But as an end user, you want to work closely with the OEM. You can't leave it solely on the OEM. As an end user, you need to understand the risk, because the risk assessment does not stop with the OEM. You continue that risk assessment process, because when that machine hits your floor, there's other risk factors that an OEM is not going to be able to see. They're focused just on the machine. But as an end user, you know where that machine is going. You know the aisle spaces. You know the operators, the people that are going to be there, how it's going to be interfaced and work with, where an OEM doesn't. So you can require it of an OEM, but as an end user, you need to be part of the process as well.
I think that's a really, really good point. Everybody's responsible for safety, but not everybody is focused on it as the part of the function of this. So it's really important to be to make it part of the documented requirements that you get at the back end, and make it a continuing part of the process. That's I would imagine an OEM that gives you that kind of documentation up front is one you're going to want to work with time and again.
Yeah, and it's not just that. There's OEMs that have been requested of that, so it becomes standard practice for them, especially with specific customers that require it. But it doesn't mean an OEM that doesn't do it wouldn't be a good partner. And that's just it, the word partner. It's a partnership. It's not a battle. So it's the OEM and the end user working together to get ultimately what everybody needs, right? It's the education factor and getting trained on what needs to be done.
Very good. Jameen Patel from Revitech Engineering says, can you please explain fault exclusion?
Sure. Fault exclusion is, I guess phenomenon is not the right word, but in certain control categories, did not necessarily claim a category without thinking about certain fault exclusions. So one of the ones that you see talked about / debated a lot is a key interlock switch. You got a mechanical key that goes into a switch where the switch has two independent contacts in there to go to your safety circuitry. So on the surface, it looks like you have redundancy, but you could have a single point of failure with key breaking and staying with the switch. So you look at, well, why would a key break to cause a single point of failure? Well, when you look at the definition of Category 3 versus Category 4 example, Category 3, you're supposed to detect as many of the single faults as possible, but you may not. And some of those may fall under fault exclusions. With Category 4, we can't do that. So we cannot have a key interlock switch for Category 4, but we can have it for Category 3. But part of that is, well, looking at a key breaking. Why would a key break? It might be because the key gets bent, and what does maintenance do? They bend it back. Well, it starts fatiguing the metal over a certain amount of time, and it could break off and stay with the switch and cause an unsafe condition. Well, if you look at, well, why would the key get bent to begin with? Well, because I have a removable door and the door keeps falling on the ground. You start looking, is that really a right application? If I'm going for Category 3 and I got to accommodate that, should I be using a key interlock switch? Maybe I use a coated magnetic or electronic switch in that application. But in most applications, you may find key interlock is more than sufficient for what you need, the safety level, but the key itself is up higher on the door is not removable, the key is protected, so the chances of it getting it bent and causing an internal failure inside the switch based off of how a manufacturer designed and built that switch, you can exclude key breakage as a potential fault of occurring in the system. However, you need to document that. So if it's a single fault that can occur and you're trying to claim redundancy with a Category 3 system, why is that a potential fault exclusion that we're not going to be looking at or testing for? It's because we put the proper hardware to mount the key to the door. The door is not going to crack or break off. The key is protected. We've done these measures to fault exclude fracture as a potential issue. So that's just one example, but that's what we mean by fault exclusion. It's the possibility of a fault that may still occur, but we can exclude it as a likelihood because of these reasons. You cannot put fault exclusions in the system out of convenience. Fault exclusions need to be justified, because what you see sometimes is, oh, you know what, I can't do that, I can't test for that, so I'm going to list that as a fault exclusion. No, that's not justified. That was convenience. You're just trying to avoid some work there. How can you exclude it as a potential fault? Well, using these measures and the chances of a fracture for occurring, because when we look at it, when you look at performance or SIL levels, they're not saying that things can't happen, it's completely impossible. It may be a very minute chance of certain things happening. What are the chances of really happening? That's why we call it a PFH, a probability of dangerous failure occurring. What are the chances of that happening? So that's what we mean by fault exclusion. I simplified that a little bit. You can get into more details about it, but that's what we're referring to.
Very good. Marcelo Caso from Bayersdorf, we wanted to know, is the performance level applicable for the component or for the overall machine?
The performance level is looking at both. You can get a performance level of component, but you're not looking at the overall for the machine. You're looking at the overall safety function. And here's what I mean by that. So if we look at the previous example that I gave with the key interlock, the safety controller, and the two mechanically linked contactors to shut down the motor. The key interlock is our input. The safety controller is our logic. The two mechanically linked contactors are our output. That is the entire safety function. So as a function, we're looking at it, that's a guard door interlock function. We went through that decision tree to say it was an S2, F1, P2. Our performance level is D. So we needed to be in a certain performance level for that safety function. Well, how do we get that? Well, with electromechanical switches, we have some additional calculations that go in there. We could have a controller that's a purely electronic. There's no electromechanical parts. So the manufacturer of that controller could supply a PFA or a PFH, which relates to a performance or SIL level potential. So you can see that in there, but that becomes one number of your overall safety function that you're adding into it. So you're looking at that performance level of that safety function, not just the individual components, but you can get a component that claims a performance level because it can achieve up to that performance level. But it's the combination of how it's installed into the safety function and looking at the overall safety function, you're trying to achieve an overall performance level of that function. And I wanted to clarify that because I believe, and if I misunderstood, let me know. But when you said is it the overall of the machine? What we used to look at before the statistical data really got a lot of win when it came to ISO 13849 and IEC 62061, so PL and SIL, we were claiming categories for a machine. Hey, this machine is control category 3. Well, with these latest standards, what they're looking at is, well, we're not looking at a machine as an overall safety function. We're looking at the individual safety functions. So ESTOP is one function and needs to be this performance level. They may share some common components. For example, they may all go to a safety PLC. That's great. That safety PLC is going to be in each one of those functions and be part of those calculations for that specific function. But the ESTOP to the safety PLC to shut the motor and dump the pneumatic power, that's the ESTOP function. We put that in there as our safety function. What performance level did we achieve? What was required? Now we got 4 doors that all go in and it doesn't dump air, but it shuts down the motor. That's a safety function, but they're all going as inputs to the safety PLC. You're looking at the door switches, you're looking at the safety PLC, you're looking at the motor starters or the variable frequency drive with safe torque off as a safety function.
Very good. I think we've got time for one last quick question. Don Magruder from Boston Scientific wanted to know, where did the control categories come from? Are they coming from ANSI? Are they coming from ISO or someplace else?
Okay, so control categories originally came from EN 954-1, which is now replaced with ISO 13849. ISO 13849 pulled in the control categories in the risk graph from EN 954 and pulled the statistical data from the IEC 61508 to pull them together to get a performance level. So the control categories are specific design architectures, and you're going to see those referenced in other standards that say, you know, this minimum safety function in this particular industry says that safety function needs to be a minimum category 3 PLD. A lot of it, what you're going to see, especially if you look at individual components from a manufacturer, you may look up the component and what standards they apply to, and they may say up to control category 3, up to performance level D, per ISO 13849. So the main area where you find that information is ISO 13849 Part 1, is where they describe control categories, but originally came from EN 954. But it has been, control categories have actually been around for quite some time now. I want to say at least a few decades from the previous standards, what people were using. But it's ultimately because that's where we stopped previous to these latest standards. We're now adding the statistical data, so our control categories are our foundation of our design and building the statistics to get to our performance level.
Very good. Well, that's all the time we have for questions today, but we have many more questions that we'll be addressing offline, and we'll be in touch with everybody after today's event. With that, I want to thank Mike DeRosier for a terrific presentation, great Q&A. And on behalf of Machine Design, New Equipment Digest, and EHS Today, I'd like to thank Schmersal for sponsoring today's event, and of course, all of you for attending this afternoon's event. Enjoy the rest of your day and have a safe day.
Thank you, everybody.